Welcome back to Mr. Soto's class, guys. We're going to be learning about limits today. We want to determine if the function is continuous at a certain point. We've already learned how to evaluate functions. So here we have an example, and it's asking you, determine whether the function 2x squared minus 3x minus 1 is continuous at x equals 2. Yesterday in class we learned about continuous and discontinuous functions. Now we want to check to see on paper, by hand, if we can determine if this is continuous. So we got to break it up into 3 steps. Step number 1, does the function evaluated at 2 exist? So this is just evaluating the function at 2. We're going to go ahead and solve it. Plug it in. F evaluated at 2 is equal to, we're going to go ahead and copy the function, but with 2 values instead of x. And then from here we just solve algebraically. So 2 squared, that's 4. 4 times 2, that's 8. 3 times 2, that's 6. Bring down the 1. 8 minus 6 is 2, and 2 minus 1 is 1. So my function evaluated at 2 is equal to 1. This passes. Step number 1 passed. So that means we can now move on to step number 2. Step number 2 is asking us, does the limit as x approaches 2 of the function exist? Okay, this is LIM, limit. So this is the new terminology that we're getting introduced to in this section. So does the limit as x approaches 2 of the function exist? And the way we figure out the limit is by drawing out a table. And since the function, the example is asking us to evaluate this function at 2, then we're going to go ahead and use the 2 as our limit. We want to approach 2 from the left, and we want to approach 2 from the right. And we want to see if they're leading to the same value. If they do lead to the same value, then the limit exists. So let's go ahead and find numbers that are really, really close to the number 2, starting from the left. If you think of a number line, we're going to get numbers that are smaller than 2. So we can immediately think of the number 1, but we want to get really, really close. So we want decimal values in there. Thus, one small number that is really close is going to be a 1.9. Then we can get closer by adding another decimal value, like 1.99. And then even closer by putting 1.999. And then we want to approach 2 from the right. So we want to get a number that's really close, like for example number 3, but we want to get even closer with decimal values. So what's slightly above the 2, it's going to be a 2.1. And then 2.01, and then 2.001. So now we're approaching 2 from the left and from the right. We're getting really, really close. Now we got to evaluate the function at these values. So we already found out what the function is at 2. We did it in step 1. It was 1. So we're going to go ahead and put a 1 here. And then we got to plug in these values into our function right here, and then see what we get from there. But with the calculator, of course, because it has exponents and subtraction and multiplication, it's going to be a lot with all these little values here. So I already went ahead and did it on the calculator, and we get 0.52, and then we get 0.95, and then 0.995. Then we went ahead and we did these values on the calculator, and we got here we got 1.005, 1.05, and then 1.52. So these are the values that we get when we start putting all these values into our function. But now let's analyze the table here. What is happening? As the x values get closer and closer to this value, number 2, that we want, we can see that the function, it increases. It goes from a 0.52 to a 0.95. So it increased by about 0.43. So it's a jump, it's getting higher. Now from the 0.95, it increased to a 0.995. So it increased again. It looks like every time we move over to the right, it's getting bigger and bigger. And it's not getting past the 1, which is good because we evaluate the function at 2 and it gives us 1. So we want these numbers to equal or get closer to this number right here. So yes, these numbers are getting closer to the 1. Now what happens when we approach this 2 from the right, when we get from the bigger numbers to the smaller, what happens here? We get a 1.52, and then it goes down to a 1.05. You see that? It decreased. And then from the 1.05, it looks like it decreased again to a 1.005. And then it looks like it's getting closer to the 1. That's what we want. It went from a 1.52 to a 1.05 to 1.005. So it looks like they're getting smaller and smaller. They're getting closer to the 1. That's what we want to see whenever we're finding a limit. We want it to get to the same value. And if the value is this, that's even better. Okay? So yes, you can tell by looking at our table that the limit exists. And then we can write it in terms like this. If you look over here, I already went ahead and I wrote it. And we write, by looking at our table, we see that as the value of x gets closer to 2 from the left and from the right, as what I had mentioned, the values that we chose, they're getting closer to 2 from the left and from the right. The function gets closer to 1. And that's what I was mentioning right here. As we chose these values of x that were getting really, really close to the number 2, the function itself, they're getting really, really close to the number 1. So we can go ahead and write in math notation like this. The limit as x approaches 2 of the function is equal to 1. That's how we write it, okay? Whenever the limit exists, we can go ahead and write the limit as x approaches 2 of the function is equal to 1. So this confirms step number 2. We're done with step number 2. We can go ahead and do our last and final step, which is step number 3. In step 3, we're checking to see, does the function evaluated at 2 equal the limit as x approaches 2 of the function? Okay, so you got to understand this terminology. If you don't understand what's happening here, if you don't know how to read this, you're going to be completely confused. I'm going to read it again. Does the function evaluated at 2 equal the limit as x approaches 2 of the function? In other words, does step 1 equal step 2? Did we get the same values? If you look back, we saw that step 1, the function evaluated 2 equal to 1. And then right now, step 2, the limit as x approaches 2 of the function is equal to 1. Therefore, they do equal to each other. So we can go ahead and write that since f of 2 is equal to 1, and the limit as x approaches 2 of the function x is also equal to 1, then we can say that the function is continuous. Oops. At x equals 2, which is what they wanted us to check. In the very beginning, it says determine whether this function is continuous at x equals 2. In order for us to do that, we need to do the 3 steps. All 3 steps need to pass. If they do, finally we can conclude that the function is continuous at x equals 2. Okay? Remember, step 1, can the function be evaluated at that point? If it can, then you move on to step 2. If it can't, then you stop there and you say that the function is discontinuous. If step 1 passes, we go to step number 2. We got to determine the limit. Does the limit exist? If the limit exists, then we can continue step number 3. If the limit does not exist, we stop there and we say, you know what? The function is discontinuous. Now moving on to step number 3, you got to confirm that the function evaluated at that point is equal to the limit of the function as x approaches that value. If these two are equal to each other, then yes, you can confirm that the function is continuous at x equals 2. Thank you guys. This is it. This is what we've learned in class. I did a couple more examples, so hopefully when you get back to class, we can continue going over some more examples so we can practice. Thank you guys.